Okay, welcome everyone to the 81st meeting of New Directions in Group Theory and Triangulated Categories. Today we are very pleased to have Arend Bayer from the University of Edinburgh, and he'll be talking to us about generalized Kummer varieties and non-commutative abelian surfaces.
Okay, thanks a lot. Yeah, thanks for inviting me, and the energy to keeping a seminar like this going. So, and yeah, feel free to use this small setting to interrupt me with any questions at any time. I'm happy to say more about any topic. And so, as the title says, the what I'll focus on today is are these what we call non-commutative abelian surfaces. And to explain what I mean by this, let's start with an abelian surface, so which is a two-dimensional algebraic variety that's also a commutative group, and so I can always think of it analytically as C2 modulo a lattice. Sorry, let me just not use lambda here. But I always insist on it having a algebraic class, or that it's a projective variety. And then I look at the derived category, by which I always mean the bounded derived category of coherent sheaves, or you can always think of it as complexes of vector bundles. And then I look, it's easy to see that the space of deformations of this category is 6-dimensional. Namely, if you look at the second Hochschild cohomology, then by Hochschild constant Rosenberg, this splits as H0 of lambda 2 of TA, direct sum H1 of TA, direct sum H2 of OA. So the first are deformation introduced by some two form. The second one are deformations of A as a not as an algebraic variety, as a complex manifold, and H2 of E are Gerby deformations. And so, of course, the ranks of these are easy to compute because TA is trivial on an abelian surface. So these are 1, 4, and 6. And so altogether, we get a 6-dimensional space of deformations. And what I'll mean by non-commutative abelian surface is a category that's a deformation of this derived category, but that still preserves some algebraic properties. And you can see immediately that we are missing out a lot by just looking at derived categories of so before I say that, let me mention that Toda, and of course, building on work of others, he really gave concrete realizations of these deformations infinitesimally. And then if you look at deformation quantizations, you can maybe also make sense of the first part of a complete local ring, but not of an algebraic space. And so here we have the 6-dimensional space of deformations. And in contrast, if you look at the moduli space of polarized abelian surface, then any component of that is 3-dimensional. Right? And so we are, in a sense, missing 3 deformation dimensions. But the first thing I actually want to argue is that we are not missing 3 dimension here, that we are just missing 1 dimension here. So we shouldn't be looking or hoping for arbitrary deformations of this derived category over an algebraic base, but really just we have to pick out some 4-dimensional space of deformations. And for motivations, let me first give you the comparison with the case of K3 surface. So K3 surface is a K-trivial surface, so the self-functor of its derived category is just shift by 2. And the fundamental group so it's simply connected. It's a K-trivial surface with trivial fundamental group. And so in this case, the Hochschild cohomology, the second Hochschild cohomology, is 22-dimensional. And the moduli space of polarized K3 surfaces, every component of that is 19-dimensional. Right, and so again, it looks like we are missing 3 dimensions, but actually there's one case where we have experience with dimensions of space 1 bigger. Namely, if you look at cubic fourfolds, so if you have a cubic fourfold, so defined by degree 3 equation in P5, then inside its derived category, there's something that's now called the cousins of components. So it's the orthogonal complement of the structure sheaf, so any complex that has no cohomology in any degree, and then also no cohomology after twisting by 1 and twisting by 2. And this is a CY2 category, right? So by CY2, I mean this property here. And for special cubic fourfold, it's equivalent to the derived category of a K3. And the moduli space of cubic fourfolds is 20-dimensional. Right, and so this is, of course, certainly a well-behaved algebraic variety. So we have a moduli space. We have a family of categories of this K3 type over 20-dimensional space. And so here we already see the analog of that one for abelian surfaces would be that we hope for well-behaved family of categories over 4-dimensional space. And I also want to highlight one feature of this construction here, namely here, inside, I mean, we always have this restriction functor here that I call, let me call this I upper star. That's the adjoint of the inclusion of this category. And from that, just applying this to the structure sheaf of a line and the structure sheaf of a line twisted by 1. This gives me a rank 2 lattice that's isomorphic to A2, to the A2 lattice of algebraic classes in this cousins of component, right? And there's a similar story for if you don't look at the cubic fourfold, but at Gushel-Morkai fourfold, so another type of Warnow fourfolds. And again, so what I want to highlight, and again, there you get a 20-dimensional family, and again, you get a rank 2 lattice of algebraic classes inside here. And in that case, it's A1, direct sum A1 instead of A2. And what I want to stress here is that this is a positive definite rank 2 lattice. And my claim is that this is also what we should be looking for more generally. So when we look at deformations of a category and we want to get something algebraic, then we should always preserve a positive definite rank 2 lattice of algebraic classes. Right? So let's look at this a little bit more systematically in the case of the abelian surface. Right? So for the abelian surface, the topological K-theory is, of course, just the even cohomology of this abelian surface, which has rank 8. And maybe let me also say that the signature of this lattice, if you equip it with the Euler characteristic pairing, then the signature is 4,4. Right? And of course, that's easy to see just from the fact that the topologically it's just S1 to the 4, and topologically the cohomology is generated by H1. And if A is algebraic, then there's at least a rank 3 lattice of algebraic classes that has signature 2, 1. So 1 comes from the polarization, and then 1 from the class of the point, and 1 from the fundamental class. So we always have 1 divisor class, and that has positive self-intersection. That's where the signature comes from. Right, and so my claim is now what we want is we want deformations of dB of A that preserve, that keep a positive definite rank 2 lattice lambda of algebraic classes. Right. So another way to say that I always have a morphism from algebraic K-theory to the topological K-theory, and the image should always contain this this chosen rank to a lattice. And basically, the claim I want to make that this is a little bit like choosing a polarization of an algebraic variety. So again, when we look at moduli space of algebraic varieties, we don't look at arbitrary deformations of the underlying complex manifold. We look at deformations that preserve a polarization or an embedding into projective space. And let me motivate this a little bit more. So one is that if we hope for an analogy of derived to value for K3 surfaces, right? So then we could hope for derived to value result via C dot HH Hochschild homology, second Hochschild homology. This gives me a class and gives me a subspace in the topological K theory of the tensor with C. Right, and here, right, insisting that these classes in lambda remain algebraic is equivalent to insisting that that this is actually contained in the orthogonal complement of this rank to a lattice. Right, so we get here this C dot HH2 inside lambda perp, which is now a lattice of tensor C, which now has signature 2, 4. Right, and as anyone who has worked with hot structures knows, is for signature 2, 4, you get well-behaved moduli spaces of these hot structures. So then we get a well-behaved some particular non-Hausdorff and algebraic period domain of lambda perp modulo some group of integral transformation of this lattice. So that's the first reason. So just thinking about derived to value already gives us motivation to restrict to such deformations. And then the second reason, let me move this down a little bit, is that we still get an interesting category. So there's an argument by Mukai for deformations of K3 surfaces is that applies in this case to show that simple objects with class in lambda will deform. Right, so I mean, if you have this family of categories and you have an object in the central fiber, in the special fiber, you can ask which objects will deform. And Mukai's argument shows that if your object is simple in the sense of having just the base field as endomorphism, just C as endomorphisms, and it's the deformations that we look at are orthogonal to its class, then this object will deform over this family. Right, and so this means at least we preserve two types of, objects that span a rank to a lattice in the topological K theory. And so that already tells us that the category will not become completely trivial. And then the third motivation is that we get that we can still hope for well-behaved stability conditions, right? So for stability conditions, we need one ingredient is this morphism from the K group of a category to C, right? So instead, so we need two linear functions on this category, and experience shows us, and also some conceptual arguments, that this is much better behaved if this can be given by Euler characteristic pairing with objects in this category, right? And so so this is much better behaved if it can be given by a pairing with in numerical K theory And in our case, this can be given with classes in lambda. Right, and so in that case, we know that say the modular spaces come with polarizations and so on, and you have base change behaves better. Okay, so on this is the first motivation why we want to look at these deformations of the derived category of abelian surfaces to get these non-commutative abelian surfaces, because there's something in between this 6-dimensional space of deformations that will just behave extremely badly over a positive dimensional base space of deformations, and the 3-dimensional algebraic variation deformations that we just get from deforming the abelian surface as a polarized algebraic variety. Okay, any questions so far before I go on to the next section? Okay, so then the second motivation for this construction comes from Hyperkaehler varieties. So, and here is where I want to explain what this word generalized Kummer varieties mean. So a Hyperkaehler variety, for today, that's just a smooth algebraic variety, M, where I assume that it's algebraic, so it comes with a polarization, but what makes it a Hyperkaehler variety is the existence of this nowhere degenerate holomorphic 2 form, and that it's simply connected, right? And so the classical example is you take a K3 surface and you take its Hilbert scheme, but today I'm instead interested in the examples coming from abelian surfaces. And so the first example starts with the Hilbert scheme of n+1 points on the abelian variety. And that's not an example of a Hyperkaehler variety because it's not simply connected. So the fundamental group of easy to see that the fundamental group of A also is the fundamental group of this A n+1. So instead, what I have to consider here is, this has a Hilbert-Chalmers map to the symmetric product of A, and this has an addition map to A, right? And so let's call this composition here a big plus. And then what I look at here is the nth Kummer variety of A. That's just the pre-image of 0 under this map. Right? And so this is the first example of a generalized Kummer variety, and really the first example of a Hyperkaehler variety that's not of this K3 type. And there's a generalization of that, so that I want to mention for completeness. But if you pick an algebraic class in the cohomology of A, and let's say that it's primitive, let's also say that it has square greater equal than 0. Then I can look at the moduli space of stable sheaves. Right, so H here is polarization. So by stable, I mean really Giesecke stable with respect to that polarization of, let's say, Chern characters or V. So in other words, I fix the numerical invariance via V. And again, this is not a Hyperkaehler variety, right? So A acts on this moduli space by translations, and A hat a dual abelian variety, which is also the group of degree 0 line bundles on A. This acts via tensoring by line bundles. And so again, this is not simply connected. And so instead, we have to do something similar here. But now the map goes not to A, but it goes to, so first there's a map to A hat. And there is a map to A. And so the map to A hat is given by, let me simplify a little bit here. So here you take the determinant of E. This gives you a line bundle. Then up to some normalization, you get a line bundle of degree 0, which is A hat. So here A hat is pig naught of A. So the degree 0 line bundles on A. And then I can also do something dual to that, which is probably the best definition is I take my sheaf, or also works for complexes E. I do the Fourier-Markov transform that gives me a complex on A hat, and then I can take a determinant there and get a line bundle on A hat. But if I iterate this construction, pick 0 of A hat, I get back A. And so that gives me an element in A. And so here the generalized Kummer variety of V associated to this situation is the pre-image of 0 cross 0. Right, and then the definition is a generalized Kummer variety, abbreviated GKV from here on, is a polarized Hyperkaehler variety that's deformation equivalent to one of these two examples. So B is actually deformation equivalent to A, so we can, it just has to be equivalent, deformation equivalent to one of them. And now, again, there's a bit of a dimension mismatch because the moduli space of polarized generalized Kummer varieties, every component of that is 4-dimensional. Right, but recall that the moduli space of polarized abelian surfaces this is 3-dimensional. Right, and so again we see that here we have one missing dimension. Okay, any questions to this part before I jump to our results? Okay, and so here is our main result. So for
Arend, just going back, these are polarized moduli spaces.
Yeah, so I always look at moduli spaces of polarized Hyperkaehlers.
Okay, so you get the 4-dimensional. Okay.
Exactly. Yeah.
All right, thanks.
Okay, right. So here our result is the following. So we start with any positive definite rank 2 lattice of algebraic classes. Right, so here I could also have said here I take only classes that where the H2 part is of type 1, 1. And then to any such choice we can associate a deformation. So the claim is that there exists a 4-dimensional algebraic variety with a quasi-finite Torelli. Maybe let me put this in quotation mark because I mean it has a map to this space of this period domain of lambda perp quotient out by the integral isometries of lambda perp and a family of Calabi-Yau2 categories over family. Sorry, let me call this D. D of Calabi-Yau2 categories over B. And it has the property that exists at B naught in B, so that when I take the base chains to this point, right? So everything is in some works for some notion of stable infinity categories, and so particularly for any morphism from another scheme to B, I can do a base change of this category to that point. And so if I do it, there exists one point so that when I do the base change to this point, then I get back the category that I started with. And moreover, the deformations are are versal. I mean, so I just mean that the coordination map is injective. The coordination map from the tangent space of B at B0 to deformations of this category is injective and orthogonal to lambda. So lambda remains algebraic. Right, and so what I mean by family of Calabi are two categories, I just mean if you take the fiber over any other point, then you also get the Calabi are two categories. And it also comes with a family of stability conditions. Over B. So basically what this is it's a stability condition on every fiber that have some well-behaved properties in families that glue them together, things like openness of stability in families and so on. And in particular, for every primitive class in lambda, so this notion of stability condition in family always comes with the relative moduli space of stable object. Then the relative, I have a relative moduli space M of V of stable objects. So what I mean by this, it's algebraic variety with dimorphism to B, so that the fiber over a given point up is the moduli space of stable object in that point. And then for every B in B, if I take the fiber this has an Albanese map. So Albanese map is basically just a universal map to a abelian variety. So its Albanese map maps it canonically to a four-dimensional abelian variety. So some deformation of A cross A hat. And the fiber is a polarized generalized Kummer variety. And right, and a corollary of that one, I mean, that would take a little bit of discussion about classifying polarization types of generalized Kummer variety, but really one corollary of that is that for every component of the moduli space of GKVs, right? So this has infinitely many components. Every component is four-dimensional. And then for every component of this moduli space of GKVs, there exists a dense open subset such that for every polarized GKV corresponding to a point in this open subset arises from a moduli space of stable objects in a K3 category. Of stable objects. And this is actually quite a contrast to the K3 type case. Where this is, I mean, for moduli spaces of stable sheaves on K3 surface, you only get 19-dimensional families. You would need 20-dimensional families, and the only way we know how to get that is from cubic fourfolds or Guschel-Mokai fourfolds.
I have a question here. So
sure.
In this last corollary, do you get this to Calabi category explicitly?
I mean, not explicit, right? So it arises as such a as it arises from this construction. So the moduli space. So whenever you have such a moduli space of GKVs, right, and there is one element in that family that arises from an abelian surface as a moduli space of stable sheaves, and so the classes of objects as parameterized gives you one class in this lattice lambda, and then the polarization comes from an orthogonal class that's also positive. And so these two together determine your rank to lattice lambda. And then I apply this theorem. But as you'll see in the following, this theorem is not very explicit. At some point, it's basically an existence theorem that they'll.
I had a similar question about, like, a question on the same theme about the family of stability conditions that you prove exists.
Mm-hmm.
So again, like, do you get them like concretely, or is it like an existence proof?
I mean, once I've told you what the category is, then it's reasonably concrete. Yeah. But
Okay.
yeah, but the part where it's implicit is a little bit in the construction of the family of categories that I'll explain. Yeah.
Okay, thank you.
Okay, other questions?
So the Albanese map is mapping to a genuine abelian variety, not a non-commutative abelian variety.
Yeah, this is mapping to a Y-type abelian fourfold. Yes.
Okay, and I didn't quite understand the contrast with the K3 case. Can you say again how this is different to the K3 case?
In the K3 type case, right? If you want a 20-dimensional family of K3 type Hyperkaehler varieties arising as a moduli space,
Mm-hmm.
right? Then and we want this to come from I mean, of course, we know that moduli space is 20-dimensional algebraic, right? But if you want each Hyperkaehler to arise as a moduli space of objects in something, then the only way we know how to do this over 20-dimensional space is to use cubic fourfolds or Guttamacher fourfolds. Yeah. Right? And that gives you infinitely many examples, but in every dimension, it only gives a finite number at most of deformation type of polarization types. And so certainly you're missing most of polarization types of K3 type Hyperkaehlers in those constructions.
So you're saying that from constructions we currently know,
yes, yeah,
we don't have this, but don't we expect it should be still true in the general case?
Yeah, but we don't have any other algebraic construction of 20-dimensional deformations of the derived category of K3s. Right.
Okay.
That work over algebraic 20-dimensional space.
Okay, but abstractly we should expect them to exist.
Yeah, exactly. Yeah, we should. Yeah, I agree.
Okay, great. Understand. Thanks.
Okay, so let me explain the construction. So that's basically the remainder of my talk will be trying to explain this construction. And so the idea is the following. So right, so we take the Z2 action on the derived category of A that's just given by multiplying elements in my torus by plus or minus 1. So I have the -1 action on A and act by pullback on the derived category. And then I look at the equivariant category. Right, so I look at the category of equivariant objects, and that's by Bridge and King-Reed. This is known to be equivalent to the derived category of the associated Kummer K3 surface. So what is S? So here I look at A modulo the plus or minus 1 action. And so this action has 16 fixed points because all the two torsion points are fixed points under this actions, of course. And then I take the minimal resolution. So basically every one of these singular points gets replaced by a P1, that's a -2 curve. And then this as a Kummer K3. And then there is a residual action. So whenever you take the equivariant category with respect to a finite abelian group, then the dual finite abelian group, that I'll insist on writing mu2 here, even though of course I'm aware that in our setting mu2 and z2 are canonically isomorphic, but I find it helpful to distinguish the two. So mu2 acts on d of s just by, if you think of mu2 as the group of one-dimensional representations of Z2, then it acts on the equivariant category just by tensoring a equivariant object with this representation. Right, so it acts on this, and in fact, Thorsten Beckmann and Georg Oberdick wrote a nice paper where they described this explicitly, this action, so which was very useful for us. And then, if you look at the equivariant category with respect to this action, then you get back the original category. So that's a result that's proved for any finite abelian group acting linearly on a linear category, was proved by Elagi. Right? And so the idea now is simply that we deform d of a by deforming d of s with the mu2 action. Okay, so what's the challenge here? The challenge is that I can't just look at deformations of S. Because deforming d of S by deforming S with this mu2 action on its derived category, then, we have quite clear cohomological criteria for when such a mu2 action deforms. And it's not so difficult to see that this is just in one-to-one correspondence with deformations of S as a Kummer K3. So in other words, as a K3 that arises from an abelian surface. And so that just corresponds one-to-one to deforming dB of A by deforming A.
Can I ask another very
Sure.
basic question?
Yeah, please do.
So you just said that there are some cohomological criteria for when this mu2 action will be deformed. What are they?
Yeah, I'll explain this.
Okay, yeah, thank you. Sorry.
Okay, so so how the question is really how to control this mu2 action on dB of S and whether it deforms. Right, and here I want to recall just a little bit the classical theory of Kummer K3s. So to every such Kummer K3, there's something called the Kummer lattice inside the H2 of S. Right, and that's defined to be the saturation of the sublattice generated by the 16 exceptional divisor. right here by exceptional divisors. Let me remind you that any Kummer K3 is the resolution of A modulo this plus or minus 1 axiom with 16 fixed points. So for every fixed point, I get an exceptional divisor in the map from S to this quotient. And then I look at the group spanned by that, but then also everything that has a multiple that's inside that. So it turns out that this subgroup is far from separated. There are many linear combinations of these where 1/2 of that class is also integral. And that's what I take. And then we instead look at the derived Kummer lattice. And so this is the saturation of the lattice inside the full cohomology of S generated by classes of the form 0 to EI 1. Again, for I equal 1 to 16. Right, and so this is this is a lattice of rank 16. Again, these classes do not generate a saturated lattice, and it's also easy to see that one can view of this. I mean, just the projection from H star to H2. So let me call this here K, and this here K twiddle. I mean, it's not difficult to see that K twiddle inside K is naturally embeds by the projection to H2, and it's an index 2 sublattice. And so in particular, because K is well-defined classically, K twiddle is also easy to describe. And the lemma that starts answering your question is the following, that namely the K twiddle is the -1 eigenspace of the mu2 action. Right, so mu2 acts on the derived category of S, and then it has an induced action on H star of S. Right, and so I can look at its invariant space, and orthogonal to that will be the -1 eigenspace, and I claim that this is the -1 eigenspace. Okay, and so I mean that's basically if you from the results by Beckmann and Overdick, which describe the involution generating this C2 action. This is an easy computation. Okay, and let me also add that the inside the orthogonal complement, this is basically identified canonically with the 2 times the even cohomology of A. Right, which is 2 times, as a lattice, it's 2 times the hyperparabolic plane direct sum form. Right, so it's not so surprising that the invariant cohomology is closely related to the even cohomology of the abelian surface, and I mean the question is basically how it relates. Rationally, it must be the same, and integrally it's more subtle how it relates, but it's not so easy to deduce this from classical results. Okay, and now the basic result is the following. And so this appeared in one version, maybe arguments like this were used by Heubrecht's Macri and Stellari, but Eddington Thomas also use arguments like this. So the argument is the following, that given the deformation of dB of S, then the involution generating the mu2 action deforms if and only if the mu2 action on the cohomology remains in Hodge isometry. And that's equivalent to saying that K twiddle remains algebraic. Right? So for any deformation of this category, as long as this mu2 action deforms on the cohomology as a Hodge isometry, which is equivalent to saying I'm only looking at deformations that are orthogonal to K twiddle in the sense of derived Torelli, then this involution deforms. And if the involution deforms, obviously we can also hope for the mu2 action to deform. Okay, does that start answering your question? Okay, and now, I mean, we kind of see what got wrong with this naive approach by just deforming S. I mean, if you deform S, then you're automatically preserving the class of a point as an algebraic class, and you're preserving the class of H0, the fundamental class, and then you're preserving the class, all the classes in K twiddle. And so altogether, it turns out that you're preserving a rank 18 lattice of algebraic classes, and that's just rank 1 too high to get a four-dimensional space of deformation of that. Okay, and so how do we solve this? So this is basically solved by the following observation. I mean, the lemma is that if I look at this 2 times lambda, right? So inside here I have lambda, and so this means inside K perp I have 2 times lambda. So lambda is still my positive definite rank 2 lattice of algebraic classes. And so look at this 2 times lambda plus K twiddle. And I look at the saturation. Then this is some standard lattice theory, or you can prove it elementary, just using four-square theorem amusingly. This contains a hyperbolic plane. So let's call this U lambda. Okay, and now anyone who's worked with derived categories of K3 surface knows immediately what to think of that when you see a hyperbolic plane. So then by all of there exists a K3T and the derived equivalence phi from dB of T. Sorry, I want to just write D on it. D of T to D of S with the property that if I push forward the standard hyperbolic plane in the algebraic cohomology of T, namely just H0 of T direct sum H4 of T, H4 of T, then this gets sent isomorphically to U lambda. Okay, and now we apply the, we look at the inverse of 2 times lambda plus K twiddle saturated. Right? This is a rank 18 lattice. And its signature is 2,16. So K twiddle is negative definite and lambda was assumed to be positive definite. And so if I look at the pre-image, right, this contains H0 of T direct sum H4 of T. So this part has signature 1, 1, right? And so the orthogonal complement always splits off as a direct sum, and when you take a hyperbolic plane. And so the orthogonal complement, let's call this lambda T, this must have signature 1, 15. Right? And this lambda T is purely contained into H2 of T. And again, it's algebraic classes because 2 lambda and k twiddle were algebraic classes on S. And the cohomological transform associated to all of for Yumokai transform is preserves algebraic classes. Right? And so now let's look at let's pull back this involution we had on S. So right, so let's say IS is the involution generating the Z2, the mu2 action on S. Then of course I can do get a corresponding involution on T. Right, and now the IT deforms with any deformation of T keeping lambda T algebraic. Right, so why is that? I mean, of course, the preimage of k twiddle is contained in H0 of T plus H4 of T plus lambda of T. But H0 of T and H4 of T, of course, automatically remain algebraic for deformations of T. Right, and so if I also keep lambda T algebraic, then I keep the preimage of k twiddle algebraic. Right, and so now what we consider is the M lambda T. So this is the moduli space of lambda T polarized K3 surfaces. Right, and so strictly speaking, I should go to some finer cover so that a universal family exists, but let me drop that here because I have to go to a cover in a second. Anyway, then, right, so here I have right, so IT deforms over an open subset of this moduli space. And then, I mean, over the special phi by this involution generates a mu2 action for which there's a cohomological criterion. And then by a result in a previous paper by myself and Alex Perry, this means there exists an entire neighborhood B, so mapping to M lambda T, so that the image contains T such that the mu2 action lifts to this family. Right, so such that, right, so let me draw this here. So I have B, then I have the pullback. So this is the pullback of the universal family. So this is a family of lambda T polarized K3s corresponding to this map from B to the moduli space. And now I have an action with mu2 acts on the derived category of this total space, linear over B. right? And then what we do is we look at the associated equivariant category, and that gives me my family of categories over B. Okay, and so that's basically the default construction for the first part of our main result, right? And then that gives us the family of categories over it, right? And as I said, it's a little bit implicit because while we can write down this involution explicitly on S, already after this conjugation to T, it becomes a little bit more implicit. But then here, this deformation of this involution, that's really an existence result, and I don't know a way of writing it down explicitly, at least not at this point, right? But then once you have this deformation of the involution, then the associated mean 2 action deforms, at least up to taking an entire cover, and then you look at the associated equivariant category. And then maybe let me conclude with stability conditions. They come from U2 invariant stability conditions on D of SB in families, right? And there's an argument originated by Roger Macri and Stellari, and recently made more precise by my PhD student Hannah Dell, and also by in a previous paper of my co-authors, that shows that that invariant stability conditions exactly correspond to stability conditions on the equivariant category. Okay, and then if you look at moduli spaces for that one, you get those. You have to prove that these all have Albanese map, and from that you get the polarized deformations of generalized Kummer varieties. Okay, let me stop here. Thank you.
Thank you, Arend. Can we all please unmute ourselves and give a round of applause for Arend Bayer? Okay, if you have any questions or comments, now is the time to make them.
So Arend, should we understand this as being if you take an abelian surface and then you take the corresponding Kummer K3, then you can deform the K3 as an actual K3 surface, such that this derived category still has this involution acting on it. And then you should regard the equivariant derived category of that K3 as being like a non-commutative abelian surface.
Yeah, except that, right, strictly speaking, in the talk I went from this Kummer K3S to a Fourier-Mokai partner T. Right, so here's where I went from this K3 surface S to a Fourier-Mokai partner T. Yeah. One can actually show that T and S are isomorphic, and so in fact, in a sense, what you're doing is, you're not taking the involution given to us by Beckmann Oberdijk's computation, but we conjugate that by an autoequivalence of that one. Yeah, and then it's exactly as you say with this additional argument. Yeah.
Okay. Because there's work. I mean, for P2, you can realize non-commutative deformations of P2 as coming from deformations of Hilb 2 of P2, just as a genuine complex manifold. You're familiar with this work of Bellman's and Rader, Theo? Yeah, that guy.
Theorichidis?
Yeah, I think that's the one. Yeah. I don't know. It's very interesting that here you're realizing the non-commutative deformations of the inner surface as commutative deformations of another surface.
Yeah, exactly. Up to this group action, right? So I mean, it's kind of surprising that these that the commutative algebraic deformations preserving the group actions do not correspond to commutative deformations of the variety representing the equivariant category. And of course, in some sense, right, yeah, I mean, we know this, right, for SSA, for P2, I think there's already paper by Chuni Lee who showed that, right, you get deformations of the Hilbert scheme by some deformations of dB of P2 that you can just write down by deforming the Bailenson quiver.
Yeah.
Yeah, that's certainly true, yeah.
Do you know how your construction relates to, I think it's work of Pantev and Bloch and Ben Bassett? They look at formal deformations of the derived category of an abelian surface.
No, I don't. But I mean, somehow, if they do get a but in some sense, it almost must give the same, right? Because our construction gives any deformation that preserves a positive definite rank to a lattice, and I would be surprised if theirs doesn't come with that, right? So if the deformation is over some formal complete DVR or so, then in a sense it could be identified up to a map from this complete DVR to our B. But I mean, of course, you can ask the same question with deformation quantization, and at the moment I don't have a concrete answer to that other than this generic answer that I just told you.
Any other questions? Let's see. Yeah, Justin, do you want to ask another question? Thought you were. Okay.
Sorry?
No, I was trying to guess if you were about to ask another question.
So this is there's no preprint yet.
No, not yet.
But this is joint with Alex and Laura and Charlotte.
Charlotte, yeah.
Okay. Great.
Okay. Okay, if there are no more questions, let us thank Arend again.
Okay, thanks a lot.
Yeah, I'm sorry for the very peculiar turnout.
Oh, don't worry at all.
Stop.